Let's go through probability. This is likely to be a long video. If I don't get all the way through it, this might even be uh, 2 videos. But probability involves a whole lot of information. There's going to be a whole lot of vocabulary coming your way. You're likely going to have to pause the video, write things down, and then come back to the video. But in essence, probability is a measure of how likely any event, some event, is to occur. Probabilities are written as fractions from 0 to 1, or decimals from 0 to 1, or percentages from 0% to 100%. So if an event is certain to happen, it's absolutely going to happen, then the probability of that event is 1, or 100%. If it will never happen, then the probability for that event is 0, or 0%. If it's just as likely to happen as not happen, then the probability of that is 1/2, or 0.5, or 50%. So probability should never be, there should never be a probability of 2. There's just going to be some fractional or decimal probability. We don't work a lot, we do occasionally, but we don't work a lot in mathematics with percentages in pure mathematics. We do in statistics, clearly. It's a political season, so there's lots of percentages rolling around in all the polls and things like that. But generally in pure mathematics, we look at the fractional certainty or uncertainty of some event occurring. So the probability of an event is written the number of ways the event can occur divided by the total number of possible outcomes. Now, an outcome is a possible result of a probability experiment, like putting different color marbles in a bag and pulling out a certain color, or rolling a dice, or flipping a coin. Those all have outcomes, and there is the probability of those outcomes. An event is a specific result of a probability experiment. So an event would be pulling a green marble out of a bag that has green and yellow marbles. And so we need to be very careful about figuring out the number of ways that this certain event that they're asking us about can occur, because that's going to be the numerator of our fraction, and the total number of possible outcomes that are going to come from the setup of that problem. That's going to be the denominator of our fraction. So those things are important. These are more than likely going to be word problems, so you're going to have to work through the words quite a bit to set these up. So probability is event over outcomes. So what's the probability of getting heads when flipping a coin? Well, the event is to get heads. The total number of outcomes for flipping a coin is heads or tails. So the number of ways to get a head in a flip is 1, and the total possible outcomes is 2, heads or tails. So that probability is going to be 1/2. So pretty simple. All right, so let's try these. What's the probability that the spinner, this particular spinner that has 4 different sections on it, will stop on part A? Well, part A is 1 possible outcome. The total number of outcomes is 4, so that's 1/4. On number 2, what's the probability that the spinner will stop on an even number? Well, there are only 3 possible outcomes, one of which is even, so the event, an even number of 2, goes in our numerator 1 time. There's 1 possible 2 out of the 3 outcomes. So 1/3 is the probability that we will spin an even number, and there are 2 odd numbers, so there are 2 events that could occur in the 3 possible outcomes. So the probability that the spinner will stop on an odd number is 2/3, or 2/3. For number 3, what's the probability that the spinner will stop in the area marked A? Well, again, 1 event, 3 possible outcomes, so 1/3. So pretty straightforward. So Lawrence is the captain of his track team. The team is deciding on a color, and all 8 members wrote their choice down on equal sides cards. So there's 8 possible outcomes for their color choices. There's the denominator of our fraction. If Lawrence picks one card at random, what is the probability that he will pick blue? Well, we can see out of the 8 cards that were written on, 3 of those were blue. There's a blue, there's a blue, and there's a blue. So there's the number of events that could come out of all the possible outcomes. So clearly the probability is 3/8, or 3/8. So the number of blues is 3. The total number of cards is 8. So the probability is 3/8. We can write that as a decimal. We can write that as a percentage. I'm perfectly fine if we write it as a fraction. So let's talk about the sample space. The sample space is a list of exhaustive, we don't leave anything out, and mutually exclusive, impossible for two different events to occur in the same experiment. It is a list of all the possible outcomes. We represent all those possible outcomes as a set. Here we have O sub 1, O sub 2, all the way up to O sub k, if there are k possible outcomes, where O is each unique, non-repetitive, mutually exclusive possible outcome. So if we're asked to write the sample space or find the sample space, we've got to determine from the setup of the problem all the possible outcomes that could occur in that problem. So if an experiment has n possible outcomes that are all equally likely to occur, then the probability of each individual outcome is 1 over n. So if we roll a die, we know that dice have 6 faces. So the probability of each number in rolling that die would be 1/6. And each one of those faces has another set of dots on it. So if we were talking about the sample space for rolling a die would be all the possible outcomes 1 through 6. If we talk about randomly selecting a student and observing their gender, all the possible outcomes for that sample space would be male and female. So the probability of any event is the sum of the probabilities of all the simple events that constitute that total event. So assuming a fair die, if we were to roll the die and see which number we were after, let's say we were after 4, the probability of a 4, rolling a 4, when you roll a die would be 1/6. There are 6 possible outcomes and 4 is only one of those events. But if we talk about rolling a die and getting an even number, well, that probability is different. It's the sum of the probabilities of all the possibilities. So there are 3 even numbers on the face of a die, 2, 4, and 6. So each one of those probabilities are equally likely to happen. So we add those up. The sum of the probabilities of all the simple events gives us the actual numerator that we're looking for in our fraction, or we can just add them up and we can get the total probability. So here on a die that has 6 faces, the probability of rolling an even one is 1/6 plus 1/6 plus 1/6, or 1/2. So we study methods to determine probabilities of events that result from combining other events in different ways. Those combinations and relationships look like either the complement of an event, which is everything other than the event. Let's say we wanted to roll even numbers on our dice. Well, the complement of that would be all of the odd numbers. The intersection of two events. Let's say we had event A and then event B. What if we wanted to choose a female out of the classroom and then we needed to choose another female or maybe a male? So that's the intersection of two events. And the union of two events looks like this. So the and the or gives us different mathematics. If we want and, it's multiplication. If we want or, it's addition. So we'll see some examples where that will become more clear. Let's talk about whether an event is dependent or independent. So if we spin a spinner and we select a marble from a bag that contains marbles of different colors, are these two events dependent on one another or independent from one another? Well, spinning a spinner and selecting a marble from a bag have nothing to do with one another. When I spin the spinner, it doesn't affect me at all picking a marble from a bag and vice versa. So these are independent events. They don't have any effect on one another. On B, it says to select a marble from a bag that contains marbles of two colors. Put the marble aside and then select a second marble from the bag. Well, that first choice of taking the marble out of the bag definitely affects the second choice. First of all, a color's gone. Second of all, my total outcomes have changed because one of the marbles is missing. If I start with 12 marbles, my first choice is 1/12 if they're all different colors. My second choice now is 1/11th because one of my marbles is gone. Those are definitely dependent on one another. So we have to pay attention to whether we're talking about independent events where they don't affect each other or dependent events where they do. So here's the mathematics. If we have two events that do affect one another, they are dependent on one another, then that's multiplication. The probability of both events is the probability of the first event times the probability of the second event. And so here's the mathematics of that. The probability of A and B happening is just the multiplication, the product of those two independent probabilities. If A and B are independent, if they don't affect each other, then the probabilities are multiplied. I think I said dependent, I meant independent on the last slide. So if they don't have anything to do with each other, then I'm going to multiply those together. Mutually exclusive. Two events are mutually exclusive and they cannot happen at the same time. So if A and B are mutually exclusive, then the probability of A or B is the sum of those probabilities. So mutually exclusive is the sum, and let's see, let's go back, make sure I say it right. And independent events is the product. So at a restaurant, customers get to choose one of 4 desserts. About 33% of the customers choose this one, 28% choose the other one. Kayla is treating herself for pole vaulting 4 feet at the meet. What is the probability that Kayla will choose creme brulee over chocolate cheesecake? So 33% choose the first one, 28% choose the second one. So let's look at the probabilities. Are the events mutually exclusive? Yes, they can choose creme brulee and it doesn't affect anybody else choosing chocolate cheesecake, and vice versa. So yes, so it's the probability of the first one plus the probability of the second one. So that's 0.33 plus 0.28. So the probability is 61%. All right, let's talk about simple events. Simple events don't really depend on other things. Here's an example. A cup is filled 100 times. Flipped, not filled. A cup is flipped 100 times. It lands on its side 84 of the 100 times, on its bottom 6 of the 100 times, and on its top 10 of the 100 times. What's the probability that it lands on its top? Well, our simple event is it lands on its top 10 out of 100 times. So that's the number of outcomes. The total number of flips, that's 1/10. There are 2,598,960 possible 5-card hands in poker. If there are 36 possible ways for a straight flush to occur, what's the probability of being dealt a straight flush? That is the number of possible straight flushes over the number of 5-card hands. So there we go. Very, very, very small probability. Roll a fair die. What is the probability of each event? What is the probability the number 3 is rolled? Well, that's one event out of 6 possible outcomes, so that's 1/6. A number not 3 is rolled. Well, there's 5 possibilities and 6 outcomes, so that would be 5/6. The number 9 is rolled. Well, the number 9 is not a possibility, so that probability is 0. And a number less than 7 is rolled. Well, that's 1 because all the numbers we're going to roll is definitely less than 7. So that kind of gives you an idea of how to turn the words into the setup of an event over outcomes. So come to class next time, and we did actually get it done in one video. Yay. Come to class next time and we'll practice probability.